I'm giving this another whirl, and I am theoretically recording this. And I put, I'm going to do it. I'm doing it in Zoom, and we'll see what happens. I think I'm being, hi, I'm being recorded, and it's not blocking my screen. And you guys don't have to worry about seeing my annoying face, but hopefully it'll record. So, you guys had your I can do it things due last night. I haven't gone through my email yet, but I've got the sort of predictable, cluster of desperate sounding looking, headers on emails from students about, something not working or, discovering, at the last minute that was something that they didn't realize they knew how to do. So if that was you, that was the whole purpose of this small stakes assignment. It was just 5 points. And if you didn't do it, do it because, you can still get something for it, but do it because especially if you discover that like, wow, I don't know how to do that. You are the person I designed this little, exercise for. So you would learn now that you don't know how to do it instead of the Sunday night when it's due in a few weeks. Okay. So your my favorite thing presentation is due in a few weeks. And again, I did that assignment because it was obvious that too many students were discovering that night they didn't know how to do it. So, anyway, I look, those are those little, this was a low stakes, just for fun, kind of thing. And some of those are many of those are very enjoyable to watch. So I'm looking forward to cruising through those, and the TA should be giving you some good feedback on that if you needed it. All right. So anyway, good job on that. And you guys have this chapter, right? The learning chapter is due tonight, I think, in Mind Is that where we are? Is that the one you're working on right now? Am I right? I think I'm right. So I'm talking about learning and memory today. Okay, so anyway, let's go. We ended up last time talking about Aplysia, that little sea slug that they used so prominently to study learning and memory, and learning about the neural sort of architecture involved with learning that simple classical conditioning and sensitization and habituation. And so we went through the process of sensitization using this little guy, all right? And it involved a little, little puff, a little water puff on this part of the siphon, and anytime that little critter gets touched there, typically it will retract that really vulnerable gill. All right. So it's just a simple little, stimulus response reflexive circuit inside this animal. And it can be sensitized by making that puff a little bit more meaningful or important. And this starts to border on classical conditioning. I understand the distinction between sensitization and classical conditioning is kind of blurry. And we're going to kind of try to tease that apart here. So, the typical thing to do there, again, the just simple reflex is, outlined there with the simple neural architecture. And I went through that, so I'm not going to go over that again. This is a quick review. All right. And habituation, remember, is the flip side of sensitization. Okay. So, this is the repeated presentation of most stimuli for a sea slug or for you. Is your brain, without any need for awareness or consciousness whatsoever, will determine that this is not relevant or an important, meaningful kind of stimulus, something we don't need to attend to. And so, a little puff of water on its gill when it's already underwater, that kind of repeated thing would just result in it going, meh, I don't really need to do anything prominent. So the gill reflex becomes, weakened. Maybe even it won't do it. That it might even habituate where it won't even retract it anymore. Okay. So that would be the habituation side of it. Well, how do you make it meaningful to the organism? Well, the way to make it meaningful is by doing a little bit of a zap, with an electrode on the, somewhere else in the body. Okay. So buzz its ass a little bit. And when you do that, the same neurons that were involved with just the simple reflex and then in the habituation get utilized differently. And if I could sum that up at this complicated system in a few words, I would say you kind of get a 2-for-1. you kind of get a 2-for-1. The siphon came in and caused a series of actions here that resulted in the normal reflex, or it kind of learning, if you will, that it doesn't need to retract as much or at all. All right. And so it's just kind of a simple chain here. There's other guys here that are, mobilized, ready to act on it, but they're not, okay, until you present the little buzz over here. All right. So when you buzz these guys, these other neurons are then facilitating. There's more neurotransmitter involved, on this motor neuron. There's more input on this motor neuron that causes the reflex. And so it becomes, we call that sensitized. Okay. So then the two stimuli together, and the one being kind of a, ouch factor, and it's just a simple reflex. All right. It just, there's no thinking here. There's no like, hey, that thing buzzed me on my ass. Maybe next time it'll hit my gill. Okay. There's no need, it's just, there's no need for, that kind of higher level kind of, processing. It's just that simple. Okay. So anyway, that was sensitization. Let's see if we can kind of and this is what happens then in the kind of long term. What facilitates that? Well, not just more neurotransmitter, but when neurotransmitters are being used, we're going to see that, the next thing that I'm going to cover is this, how do we go from this temporary result to a learned thing? Remember, learning is this, relatively permanent change in behavior due to experience, okay? So, this prize now had the experience of getting its butt buzzed and its siphon puffed. How does this, translate into a long-term thing? Well, simply, for now, simply more synapses will get formed in that series of chains. Okay, so it'll result in a long-term sensitization because, again, it's it went from like a 2-for-1 to a 4-for-1 or a 6-for-1 or something. It just gets magnified here by more. Not necessarily more neurons aren't being born, but more connections between the neurons that are there. Okay, so that's what the long-term learning looks like. Okay, so how does that differ from classical conditioning? All right, so let's see if we can kind of tease that apart a little bit. So we're going to kind of do the same thing here. We're going to have a mantle shelf touch. All right, and that's going to predict. That's going to serve as that puff on the water puff on the siphon on the mantle is going to again that's going to become a conditioned stimulus, which for now is just causing either habituation or sensitization. It's now going to serve as a signal. Okay, so it's not occurring simultaneously with the little tail buzz. It's going to be followed by that tail buzz. All right, so it's going to become a signal. That's what classical condition is. It's learning an association between stimuli. It's learning that, hey, this, again, we don't have to add consciousness to it, but we're humans, so we always do that. So it's as if the conscious brain, which isn't necessary, is saying, hey, this predicts that. Those hands on that clock, which are meaningless and neutral for much of our life until we learn how to read them, they signal certain important things. This little puff on my siphon is going to signal, a little buzz on my butt in a moment. Okay, and so the buzz in the butt already elicited gill withdrawal, and in fact, repeatedly, it would result in sensitization of it. More and more powerful withdrawal. Now it's going to be able to. Now the puff is going to be able to do it alone. That's what classical conditioning, right? You ring the bell, you present the food, the dog drools. You ring the bell, present the food, the dog drools. You ring the bell, whoop, don't present the food, the dog drools anyway, right? So that's exactly what we'll see here. You do the puff, and again, where the puff was before all by itself, leading to the opposite habituation. Now with the combination of it's now become a signal for an ouch factor. It now serves to not only sensitize the critter, but make it learn that this is a signal. So it's going to do it in the absence of the shock. All right. So neurally, that looks just like this. All right. Same circuits, pretty much the same thing. It's almost the same think it might be the same diagram we were just looking at. So you have those facilitating neurons that are just kind of waiting for signaling. You got the direct reflex here, you know, a sensory neuron landing on a motor neuron to cause the withdrawal. And then you got, you know, a sensory neuron on the butt area, okay, and on the, you know, on the mantle area, okay. And those things are all these, you know, those two are, they're communicating with this, you know, interneuron, which is going to kind of, you know, serve to help facilitate this learning process. Okay. So, you know, in the control procedure, without the tail buzz, you know, it was just resulting in this, a normal withdrawal. And again, repeatedly, that would actually just result in habituation, but we're just, you know, we're not talking about that now. All right. So now we do both. And that's the conditioning phase. So when they're both happening, the inner neuron gets involved and it's spitting out its neurotransmitter. So that results in more input on the motor neuron. And see, this isn't conscious. There's no critter, there's nothing in there saying like, hey, you know, watch out. Nothing. It's just more neurotransmitter. Just more neurotransmitters. All this process takes, okay, on that motor neuron, on that gill withdrawal reflex. All right. So that's what's going on in the conditioning phase. Well, and again, this is, you know, remember the classical conditioning requirement is that you have the signal it's got to proceed or at least be at the same time. It's best if it proceeds. Okay, so watch that again. Okay, you know, we did puff, then bzzt. Okay, if you did bzzt, then puff, the shock is already its own signal. It doesn't, you know, the puff is going to get lost. It's not even going to notice the puff. Okay, the puff doesn't become learned. All right, you present the food before you ring the bell. The bell isn't going to be heard. The dog's already gobbling and drooling. Okay, classical condition requires, you know, this neutral stimulus precede or at least be at the same time. Better to precede it, and not by a whole lot of time. Too much time beforehand, and it's like, you know, ring the bell. Come back tomorrow and present the food. The bell's not going to, you know, the dog's not going to remember, like think, hey, that bell means I'm getting fed tomorrow. Or that bell means I'm getting fed in a minute even, okay? You know, too much time and you lose the ability to have classical conditioning. Okay, so puff, bzzzt. And then I don't have a little action here. You got to imagine, boop, and then they'll go, and then the withdrawal of the gill. Okay, then finally, when it's, you know, to demonstrate that it's been classically conditioned, you have the bzzzt. And that's not even right. That's not I got the wrong word there. That's the puff. Bzzzt is supposed to be puff. Okay, so oops, I goofed up on my PowerPoint. Pretend that, you know, that's puff, not bzzzt. Okay, there's no shock. Okay, so the puff on, you know, again, way back, you know, over here, if you puffed on either, you know, if you puffed on the mantle, you know, it was just nothing. It was control. It was, if anything, it was habituation. Okay. Now puff on the tail or the mantle. This is the mantle, whatever the mantle is, near the siphon. Okay. And this picture's all out of whack here. The butt's, this looks, I don't know. The mantle's above the butt. The butt's up here for some reason. Okay. So anyway, we're not shocking the butt. We're just puffing the mantle. And it now results in this, like, just as strong a withdrawal as when the shock alone happened. Okay, so the animal has now learned, hey, that puff is just as meaningful to me as the tail buzz. Okay, so I hope that made a little bit of sense what the difference between sensitization and classical conditioning is. It's real blurry. It's real blurry. It really boils down to just the timing of the two. One's got to precede. It means it's predicting. It's being associated with the delivery of the other. All right, that's what's learned. That's what the association is. Okay, the animal is learning, and it doesn't have to be conscious. Most of what you are classically conditioned to has not been conscious. Okay, you have not been fully aware. You can classically condition human beings without them even knowing it's going on. Okay. All right. Can you operantly condition an invertebrate like a snail, slug? Can you remember what operant conditioning? Operant conditioning is this, the animal. I know what you're doing. Attendance. Thank you. I would have forgotten because it's Monday. I'm getting attendance going. Operant conditioning is learning that there's something that you can do that has, that will have an effect, that will have a result. Okay. And remember, there's three possibilities when an organism does anything. Something favorable happens, something unfavorable happens, or maybe most of the time, nothing at all happens. All right. And we're really, in operant conditioning, we're really concerned with the favorable and the unfavorable, the reinforcing and the punishing. Okay. So is there anything a sneeze snail, I cannot say that. Is there anything a sea snail can do that, is an example of operant conditioning? Can it learn to operate on its environment and make shit happen? Okay. And the answer is yes, but it's very, very limited. All right. And I'm getting attendance going like I promised. So for operant conditioning to happen, the organism's got to be able to behave in non-stimulus response, in reflexive only, let me say that all over again. An animal that only engages in reflexes isn't going to engage in operant conditioning, because operant conditioning requires I don't want to say the choice because that makes it sound like it's got to have consciousness. You don't have to have consciousness for any of this, right? But it's got to have a repertoire of behaviors, some possible options for behaviors. If you're just doing if you're just kind of wired like a little robot, okay, then you're not selecting a behavior. You're not sort of spontaneously engaging in behavior. I don't know if there are any good examples of critters that are only reflexive. Maybe, I don't know, maybe single-celled organisms maybe are just purely reflexive. I don't know. We humans definitely have some selection in our behavior. We spontaneously do things like, oh, I'm wiggling my finger now. All right. And then we can assess again, non-consciously, we can, the consequences of that action can circle back to either cause that to increase or decrease its occurrence. Okay, so this slide's supposed to be meaningful. It's from your book, and I'll do my, it's kind of awkward, but this Aplysia, somewhere in its brainless head has a mouth, okay, and it's got the equivalent of teeth, apparently, okay. It doesn't have teeth, but it bites, it eats stuff, all right, it eats for a living, all right, so it chews seaweeds and kelp and shit, okay, so it's got a mouth, it bites, all right, so there's a behavior, that it kind of just can, it's got some flexibility in how it eats, all right, because it's a fairly smart critter, so it's not just simply, reflex, ooh, bite, reflex, bite. It can engage in sort of a spontaneous sort of looking behavior. All right. So anyway, they can let me see if I can make some sense of this. So, in the control condition with no food reward, these little round dots are, these graphs mean, they're in time when a bite occurred. Okay. And the little green triangles mean they administered seaweed juice as a reinforcement. Okay. Seaweed juice, yum. Seaweed, Aplysia is just like, oh, that's great stuff. Okay. Normally I got to chew this stuff to get that juice. Okay. So it's like, you can deliver the juice and it's like, it's like your caffeine on a Monday morning for a sea snail. All right. So anyway, you can administer that as a contingent reward. So if you just, here's just some spontaneous biting and nothing's happening. All right. And, in the control condition, if you never administered the seaweed juice, the biting just kind of occurs sort of randomly, okay, But if you give a contingent, let's jump down to the bottom. No, let's jump to the middle. All right. So if you give a contingent reward, meaning the reward is dependent on it biting. So if it bites, I don't know how you assess that this guy's biting, but they know. All right. I don't know if they're watching it or they got to wire it up. Somehow they know the thing's biting. And every time it bites, they squirt a little bit of the seaweed juice, I don't know, presumably in its mouth. And the guy's like, ah, all right. So what is the guy going to do? The guy, take away even the need to like deliver the juice, and then pretty soon the guy's like biting like mad. It starts to increase the biting behavior because it was learning like, hey, like, look, it bit, nothing happened, it bit, oh, seaweed juice. Some time went by, it bit again, oh, seaweed juice, bit, seaweed juice, bit, so each time it learned like, hey, every time I bite, I'm getting a little blast of seaweed juice. Pretty soon it's just biting like mad, okay? But if you make it a non-contingent, you're administering seaweed juice, but look, they're just doing it like on a set schedule of time, like every, I don't know what time that is, every second or something, a little squirt of seaweed juice comes, all right, independent of when it was biting, okay? So look, it wasn't getting it like associated with, so anyway, it's going to be a lot like control, okay? That was long. Yeah.
Is contingent reward like training or?
Is contingent what?
Contingent reward training. It's a lot like training a dog, right?
Exactly like training a dog. Well, there's good training of a dog and there's bad training. Like it's successful training of a dog, So if you want to teach your dog to shake hands, all right, you have to, the reward that you deliver the dog has to be dependent upon, contingent upon it doing something resembling shaking hands, okay? And that's a whole shaking hands is like, I don't want to go, I'm not going to go into all the details about that. So you use what's called shaping in a situation like that to like, if you're just waiting for a full-fledged, bona fide, good-looking shake from the dog, you might be there a long time. So, if it lifts a paw off the floor, it's like, hey, that's a good start, and you give the reward. The reward might be a little piece of biscuit, or it could even just, dogs work for good dog, good boy, good girl, they learned that inflection, you could say, anything, you think they know your words, but they really just kind of know the tone of your voice. So you say, you say like, want to go for a walk, or you want a snack, good boy, you have a little inflection in your voice, and the words actually don't matter as long as you say the right inflections. Your dog will work hard for the inflections, okay? And so you can shape that behavior by getting more and more strict and requiring better and better approximations to the actual shaking of the hand, or rolling over, or sit up, or play dead, or don't crap on the floor inside, go outside. Whatever behavior you're trying to shape, you have to reward successive approximations, okay? This is real simple. They didn't have, they're using a natural existing behavior in this guy, biting, okay? It already does the biting. But they can at least demonstrate that, look, our reward can shape how often we get this guy to bite. And it probably could go further. You could probably teach this guy some additional, like, hey, there's times that this will work and times when it won't work. Like you could associate, I don't know, you could have some stimulus in its environment that the snail can be aware of. I don't know if they've got eyes or not. I don't know if it could be a visual stimulus. Maybe it's just warm water versus cold water. Hey, if the water's warm, then biting's going to pay off with the seaweed juice. But,
is it the same with like punishment?
Yeah, you could like presumably punish this guy. So like, the tail shock is pretty, nobody likes tail shock. Tail shock is aversive to everything. Okay. So you could probably teach this guy like, hey, when you bite, don't bite. Don't bite, don't like your dog, right? People don't, train their dogs not to bite, by doing something that's aversive, like shock collars, okay? Or rolled up newspapers, okay? Tail slaps, stuff like that, okay? You can make a behavior contingent upon the punishment, all right? So, you could eliminate biting by shocking it every time it bites, okay? Animal's not going to live very long, but not because of the shock, but if it stops biting, it's not going to eat. All right, so anyway, yes, you could even get operant conditioning even in a simple critter like this guy. Okay, I think we're done with this guy. Let's put that guy back in the water and leave him alone, poor little dude. So now we know like roughly how this happens. How does it actually happen? So for them or for us, this process of, I already hinted at it. It's about developing It's about developing new synapses. It's about enhancing the ones that exist and perhaps growing more synapses and or at least more receptors in those synapses, the receptors for neurotransmitters, all right? So this is almost always an excitatory process rather than an inhibitory process, but even in inhibitory pathways, it's all about more receptors and or more synapses, or both, okay? So this process of how this begins to happen has been termed long-term potentiation, LTP. All right, so it's the basic process for learning and memory. So we'll jump to us and look at how this occurs in the human brain. All right, so and it's our best example of this is going to involve a receptor that we took a peek at back in chapter 4, I believe, the NMDA receptor. Don't ask me to tell you what NMDA stands for. I forget. So the NMDA receptor is a receptor that's a glutamate receptor system. Okay, remember glutamate. Glutamate is the most prevalent excitatory neurotransmitter used in our brains. All right, so learning is very much a glutamate process. All right, so let's see how this happens. So the hippocampus, we're moving from one H, from the hypothalamus to the hippocampus. You're not the first student to get those two mixed up if you have, all right? They're near each other. They sound almost similar. You hopefully now remember what the hypothalamus is, and you hopefully remember, thanks to your hippocampus, what the hippocampus is, all right? So I always tell students, this is the easiest way to remember, like, hippocampus. Campus. The campus is where you go to learn. The hippocampus is where you go to learn, okay? The hippocampus is that important structure involved with learning. It's not where the memories are going to be stored, it's how the memories are going to be stored, all right? So the hippocampus is almost invisible in this image right here. It's project on the screen. It's this, ghost image right here on Halloween. The head of which is the amygdala, all right? The amygdala we'll come back to. The amygdala is important for emotions, and so emotions are a very important part of learning. So anyway, maybe not surprisingly, the head of the the amygdala is not technically the head of the hippocampus, but I like to call it that. It's right there at the head end. It's kind of serving as the head of the hippocampus. All right, the hippocampus means seahorse in Greek. Okay, it looks like a seahorse, lounging on its back with its tail, up in the air. All right, so that's what it looks like from the side. From the front, it looks, like this. And then the hippocampus has just kind of continuous, it's continuous with the cortex. And so there's folds of cortex that are around it. All right, and then near it. So this parahippocampal cortex. Okay, para means around. It's around the, near the hippocampus. All right, so let's, this image is sort of a zoomed in slice of the hippocampus here. All right, so you got different areas. It looks like this sort of like fold. All right, these folded sort of layers of tissue connecting to the fornix and all kinds of good stuff. All right, okay, so this is where this process that I'm about to describe is sort of taking place very prominently, all right? This long-term potentiation, all right? So I don't like this image. It's not very helpful. This is an axon and a dendrite, I suppose. And these waves are supposed to resemble action potentials coming in, all right? So, if you have a weak stimulus, you have, a little bit of buzz happening, all right, from, across the synapse and extending on into the postsynaptic dendrite. Apply a strong stimulus, and it might just be because more action potentials are coming in more rapidly. All right. That's not a very helpful image, but so that's kind of what's going on here. Okay. So it's all about communication. It's all about action potentials. Memories are about like, hey, active signaling. It's a excitatory process. This is the equipment that they've used apparently. All right. So you got a bunch of stuff. All right. You take out, they removed hippocampal slices and kept it alive in petri dishes, and you got electrodes and recording all this shit. So they can kind of, we have learned by studying, the activity of these neurons at the neuronal level in these slices. These are little slices of hippocampus. All right. So what is happening here? What's happening here? Back to that NMDA receptor. Okay, so let me remind you how the NMDA receptor works, because it's one of those. Remember we learned that there's quick synaptic responses and ionotropic responses, and then there's slower ones, metabotropic, action potentials, not action potentials, synaptic activity. Okay. And the metabotropic are the slow ones. The slow ones could be just seconds long, or it could be, days, maybe even weeks, causing changes that occur over days and weeks. Causing the cells to, do DNA stuff and make proteins and stuff that takes days and weeks to go. All right. So it can be really lickety split, and it can be real long, but not ionotropic. Ionotropic, remember, an ionotropic response is a neurotransmitter lands on the receptor, that receptor pops open or snaps shut. So it's immediate, snap. All right. So this guy uses the NMDA receptor is a complicated metabotropic system that's really, it's a combination of ionotropic and metabotropic. All right. So glutamate is, again, the neurotransmitter used in these systems. All right. So it comes in here and it hits the NMDA glutamate receptor. All right. So the glutamate lands in it. And when that thing is at rest, it's got a little piece of magnesium, stuck in it, blocking the door. All right. So glutamate landing in it will cause it to let go of that magnesium. All right. So the magnesium will, let the door open up, and, calcium 2, positive, remember the inside's negative, the synapse itself is positive relative to the inside. All right. So that all those positive ions like calcium is kind of dying to get in. So magnesium was blocking the channel, and now it's out of the way because of the glutamate. So calcium can come rushing in, but calcium isn't causing the signaling. Calcium is only a part of the process. Okay. So it brings in its positivity, and its positivity causes a couple of things to happen. So, one of the complicated things that causes it to happen is it starts what's called a second messenger system. It causes this production of something called protein kinases. Okay, so that protein can drift over, and it can do two very complicated things. The simpler of the two things it can do is it can drift over and hit this other receptor, which is closed, and until glutamate landed on it. And so it had to have the combination of glutamate and now plus this protein kinases causing it to open up, and now sodium can come in. So we had calcium coming in, now we have also sodium coming in. So we've got this like lots of excitation happening. So there's the kind of ionotropic part of this, this like immediate like rush of positivity coming in, okay? So that's gonna help things happen, all right? So the other thing that protein kinases is doing is it's actually, this is the weirdest kind of neat thing. It's drifting across back, feeding back, and it's having it's serving, this we got like, we're not positive about this yet. The speculation is that it's serving as some kind of messenger back to the presynaptic neuron, telling it to like do more shit. Okay. So it's a double, it's not only, so the learning, the thing that caused this action potential to start is causing, it's continuing. So we see now how it's continuing with this double, receptor system, but it's also feeding back to kind of enhance it. So that's kind of the long-term potentiation part of this field. Okay. So the net result is this, this will, with repeated buzzing of learning, this will help facilitate the learning. Okay, let's see if somebody else can explain that better and differently than I do. We'll maybe have to close with this.
Welcome to 2 Minute Neuroscience, where I explain neuroscience topics in 2 minutes or less. In this installment, I will discuss long-term potentiation, or LTP. LTP is a process by which synaptic connections between neurons become stronger with frequent activation. LTP is thought to be a way in which the brain changes in response to experience, and thus may be a mechanism underlying learning and memory. There are a number of ways in which LTP can occur. The best known mechanism involves a glutamate receptor known as the NMDA receptor. In NMDA receptor dependent LTP, glutamate release first activates a subtype of glutamate receptor known as the AMPA receptor. NMDA receptors are found nearby these AMPA receptors, but are not activated by low levels of glutamate release because the ion channel of an NMDA receptor is blocked by a magnesium ion. If frequent action potentials cause greater stimulation of AMPA receptors, however, this will cause the postsynaptic neuron to depolarize, which eventually causes the voltage-dependent magnesium blockage of the NMDA receptor to be removed, allowing calcium ions to flow in through the NMDA receptor. This influx of calcium initiates cellular mechanisms that cause more AMPA receptors to be inserted into the neuron's membrane. The new AMPA receptors are also more responsive to glutamate and allow more positively charged ions to enter the cell when activated. Now the postsynaptic cell is more sensitive to glutamate because it has more receptors to respond to it. Additionally, there are thought to be signals that travel back across the synapse to stimulate greater levels of glutamate release. All of this makes the synapse stronger and more likely to be activated in the future. This process is also associated with changes in gene transcription in the neuron, which can lead to the production of new receptors or modifications to the structure of the cell. These changes seem to be important for making the increased responsiveness of LTP long-lasting.
Okay, let's make this really meta here.
Polarize, which eventually causes the voltage-dependent magnetic.
Let's make this all really meta because, this would be like the coolest example of long-term potentiation I can think of. I want to help facilitate long-term potentiation of long-term potentiation, okay? So for you to remember how long-term potentiation works, you have to have long-term potentiation be engaged, okay? Because you need to, learning is what? Learning is this creation of new synapses, the strengthening of existing synapses, creation of new synapses, the strengthening of existing receptors, the increasing production of more receptors, combination of the four options, all right? And I forgot to mention that when I was talking about it. So, we saw again how this system worked here, but I want to jump to this image. So I forgot to mention this. So the protein kinases, is thought to circle back to cause that thing to release even more glutamate. Glutamate started this whole process. And it's like, hey, bring more of that shit. We like that. That'll help us learn and remember this. Okay. So that's, again, no consciousness, but that's as if what's going on. But the other thing I forgot to mention is that process triggers this long-term process of growing new receptors. So more of these little protein blobs will get formed and embedded right there. So there's more of them, right? Logically, if there's more receptors, this can more easily happen. So if I want to remember something, I got to have more receptors, more synapses, maybe more receptors with more synapses. The more of more is betterest, okay, for you to remember something. So the more this can happen, this long-term potentiation is kind of a cyclical process. Learning takes time, much to our chagrin. Sometimes learning is it's so fast and rapid, and sometimes I can so readily think of bad things that happen, and I just why can't I remember this embarrassing thing? It happened one time, and I remember it forever. And then I want to remember, what are the steps for long-term potentiation? And I got to gruel myself through this process to make it repetitive and stick. Okay, so sometimes, learning just happens immediately, and sometimes it just takes. It's like an annoying paper cut. Learning is like paper cuts. You got to wait for them to heal. Okay. Sometimes it takes a while. So now you know a little bit more about the process by which that happens. It's this long-term potentiation. How was that? Exhausting for a Monday? Okay. Trick or treat. We're done. Okay. Thank you for being here today.